Okay, there is a problem. Phi from Z to Zn by phi of m equal to m modulo n is a homomorphism. To prove that it is phi is a homomorphism, second, find its kernel. Third one, the factor group or the quotient group Z by n is isomorphic to Zn. There are three questions. First, to prove that phi is a homomorphism. Okay. For we select two elements x, y in Z, then find phi of xy. Phi of xy equal to xy when x less than n, y less than n. In this case, x means phi of x and y means phi of y. If x and y are both less than n, then phi is a homomorphism. In another case, if x is more than n and y is more than n, so x can be written as k1 into n plus r1 and y can be written as k2 into n plus r2. Okay, for example, n is 20 and x we selected as 43. Then x can be written as 2 into n, that is 20, plus 3, where 3 is the remainder when 43 is divided by 20. In similar way, x can be written as k1 n plus r1 and y can be written as k2 n plus r2 because x is more than n and y is more than n. Then phi of x is equal to the remainder when x is divided by n, that is r1. Phi of y equal to r2. Given that phi of x equal to or phi of m equal to m modulo n or x equal to m modulo n, where m is the remainder when x is divided by n. Okay. Then xy equal to k1 n plus r1 into k2 n plus r2. After multiplication, we get k1 k2 n square k1 r2 plus k2 r1 into n plus r1 r2. That is, r1 r2 is the remainder when xy is divided by n. This is a multiple of n, this is multiple of n, then remainder part is r1 into r2. Therefore, phi of xy equal to the remainder r1 r2. What is r1? r1 is given as phi of x and r2 is given as phi of y. In this case, phi of xy equal to phi of x into phi of y, or phi of x star y equal to phi of x star phi of y, that if I preserve the operation in the second case. Similarly, in all case, phi of xy equal to phi of x into phi of y. Therefore, phi is a homomorphism. Okay, next to find the kernel. Then what is kernel? Kernel of mean the set of in domain such that whose image is the identity element. Here the codomain is Zn or the codomain group is Zn, the identity element in that is 0. Therefore, x can be written as a multiple of n. Assume, for example, n equal to 20. If phi x is equal to 40, then remainder is 0. 20, remainder is 0. 60, remainder is 0. The result is the remainder when our x is 40 is divided by our n here 20 example. In similar way, phi of x equal to 0 implies x is a multiple of n, that is kn, implies an implied. Therefore, x equal to x is member in, where x is a member in the group generated by n, which implies kernel of phi is equal to the group or the set generated by n. That is, our kernel is the set generated by small n. And also we have every kernel is a normal subgroup. Every kernel is a normal subgroup. Therefore, our set bracket n is a normal subgroup. And by theorem, phi from Z to Zn is a homomorphism and bracket n is a kernel. Then by theorem 10.3, the quotient group Z by bracket n is isomorphic to Zn. By theorem 10.3, phi is a homomorphism and this is kernel and also normal subgroup. Hence, they are isomorphic. Hence the problem. Okay.